Okay, now we are going to find all of the possible rational roots of our polynomial, and this is called I'm pretty sure it's called the rational zeros theorem or something like that. So what you do, you get your leading coefficient, which is 1, and your lagging coefficient, which is -6, and you remove negatives, and then you find all of their factors. And what you do, you put it as a fraction. So what we do, we get all of our factors of 6, which is 1, 2, 3, and 6. And then we do it all over all the factors of 1, which is just 1. So now what we do, we can just remove that. And then we know that it's going to be plus or minus any of these. So our possible roots are going to be -6, -3, -2, -1, 1, 2, 3, and 6. Those are going to be all of our possibilities. So now what we're going to do, we're going to use Descartes' rule of signs. And so this is a plus here. What you do, so there's a sign change here. So that's a sign change. Then there's none, none, and none. So we have one sign change, which means there is one positive root. And so now what we do to find the number of negative roots, we're going to put p of -x into our function. So we'll have p of -x equals it's going to be x to the power 4 plus x cubed minus 5x squared plus x minus 6. So now we've got to find all them sign changes. So the plus here, and so here's none, there's one right there, there's one right there, and there's one right there. So we have 3 there. And now, so we got 3. So there's 3 okay, so now what we do, we gotta keep subtracting 2 until we get to 0. So 3, then we get 3 subtract 2 is 1. So we either have, and then after that you get -1. So we either have 1 or 3 negative roots, or negative rational roots. Okay, so now we know how many of each we have, which means we either have one positive root and one negative root, which would mean we'd also have 2 imaginary roots, which are conjugates of each other, and that, or we'd have 1 positive root and 3 negative roots, so we won't have any imaginary roots. So we know how many we have. Now we just kind of put numbers into our equation, see if something works. So we can start with 1 and -1, why not? So p of 1 equals 1 subtract 1 subtract 5, so they've got -5, subtract, so that's -12. And then p of -1 will be 1 plus 1, that's 2, subtract 2 subtract 5, which would be -3, minus -1, which would be 4, subtract 6, which is -2, I do believe. So we know neither of these are going to be roots, so we'll just get rid of them. So we can just erase these, we know it can't be either of those. So now, let's try another one. Let's try -2. P of -2. So we got 16 plus 8, which is 24, minus 10, which is -14. Oh, sorry, I did something wrong. We have 16 plus 8 minus 20. No, we got 24 minus 20, which is, oh my goodness, okay. 24 minus 20, which is 4. Then we got minus -2, which is 6, and minus 6, which is 0. Okay, so we found one. Now, since we have -2, what we do, we use synthetic division. So we have -2, put that there, and then we have 1, minus 1, minus 5, minus 1, minus 6. So drop the 1, -2, minus 3, multiply that, and you get positive 6. Add those, you get plus 1, and put that there, you multiply, you get -2, then you get subtract 3, and then you multiply those, and you get positive 6, and that gives you 0 remainder. And there's a nice little suppressed sort of polynomial without all of the exponents and stuff written in. So now, yeah, we'll write our suppressed polynomial. We get x cubed minus 3x squared plus x minus 3. So there we go. Now we need to find, so now we know, so we have, here are going to be our roots. I'm going to write them here. We have, so far we know we have x plus 2. There's one. Now we can use our rational zeros theorem again to find all the possible ones for this, which is also going to be some of these probably. So we have, we'll call this f of x, just because. Okay, so now we will use our fancy theorem. So we have 1 or 3 plus or minus 1 or 3 over 1. So we have, we've already tried -1 and 1, so we know it's either positive 3 or -3. So now, since we need at least one positive root, and we can assume that we only have one negative root because we don't have any options, so we'll try positive 3. So let's synthetically divide that again. So let's put a fancy thing here. And just do this. We'll put our positive 3 in there. And then drop the 1. Multiply that by 3, you get 3. And that is 0. Multiply that, you get 0, and you get plus 1. Then you multiply that, you get plus 3. And you get 0 remainder. Or you get that remainder 0. So now we'll write our more suppressed polynomial, and we also know that we have x subtract 3 there. So let's write that nicer. Okay, so now we have x squared plus 1. And since that isn't like a perfect square or anything, we're going to have to, I guess you could use the quadratic formula, but this one's pretty simple. You should know how to do this one. It's just I, which is going to be negative I, and I. You just get plus or minus I. So now we know we have x minus I and x plus I, which are conjugates. Then we have our factored form of our polynomial. So what else? Oh yeah, the multiplicities of each root. So, multiplicities of each root. So a multiplicity is how many times or it's kind of like how redundant a root is. So this one is only there once. This one's only here once. This one's only here once. This one's only here once. But if we had like x squared or something, you'd have two roots. Both of your roots would be just like right there, or x-intercepts would be right there. So you'd have like x and x. So that would be like multiplicity 2. So like you basically have x squared, which has multiplicity 2 because it multiplies by itself 2 times. Or if you wanted, if this was in here twice, if you had a square there, this would be 2 as well, but it's not. So everything's pretty unique there. So we have multiplicity of 1 for every root here. So, yeah. Thanks for watching.